Hello, my name is Courtney Payne, Associate Editor at ASHRAE Journal. Thank you for joining us for today's webinar, part of the ASHRAE Journal Supplier Webinar Series. The series provides information of interest to ASHRAE Journal readers and others about products and technology of interest to industry professionals. ASHRAE does not review supplier webinar presentation. The following presentation has been prepared by Belimo on the subject, How to Protect Your System and Save Money by Understanding the Effects of Glycol on HVAC Systems. Today's speaker from Belimo is Philip Hollick, Belimo's top expert on sensors. Philip has been working in Research and Development Department at Belimo since 2005. During this time, he has investigated various technologies and application fields for sensors in the HVAC market. He has gained a strong expertise on flow measurement for both air and liquids. Philip has successfully led both technology and industrialization projects, greatly contributing to Belimo's success in the sensor business. He is currently counseling Belimo's Executive Committee on Sensor Business and has an active role in defining the technology roadmap for sensors at Belimo. Philip started his career at Sulzer Hexas as development engineer for fuel cell systems. Philip studied at several institutions, including the University of Ulm in Germany and Chalmers University of Technology in Sweden. He received a master's degree in electrical engineering from Karlsruhe Institute of Technology in Germany and a bachelor's degree in economics from the University of Zurich in Switzerland. Philip, the microphone is all yours.
Thank you, Courtney, for this kind introduction, and also a warm welcome from my side. How to protect your system and save money by understanding the effects of glycol on HVAC systems. During this webinar, I'm going to explain to you how glycol is affecting system efficiency in HVAC systems. We start with some fundamentals. Then I'm going to show how glycol is used in practice. Afterwards, we learn how to measure heat transfer with water, and especially what is the difference when glycol is used. At the end will be a short summary and some time for questions. So we start with some fundamentals. I just see there is quite a delay between what you see and what I see, but I continue anyways. Well, the fundamentals are necessary to understand heat transfer in HVAC systems and to understand the critical properties of glycols. The easiest example for heat transfer is from your boiler to your radiator, if you have a water-driven heating system. You have a boiler that is heating up the water, you have a pump transporting it, then you have a radiator that acts as a heat exchanger, so air is being warmed up and the water is cooled down. Then the cold water goes back to the boiler. Another example is an air conditioning system, consisting of a chiller, a pump, and a heat exchanger, for example, in a rooftop unit or a fan coil unit. In the heat exchanger, the cold water from the chiller is being heated up from the hot outside air, and then the warmer water goes back to the chiller again. In both cases, we're talking about heat transfer, once from the boiler to the radiator and once from the heat exchanger to the chiller. So heat transfer can be used for both heating or cooling applications and describes the transfer of thermal energy in general. Now, how do we measure it? It is kind of self-evident that the temperatures in the supply and the return pipes have an influence. it is also easy to understand that the flow plays a role. Last, the fluid has an effect. As you can imagine, an air heating needs much bigger pipes than a water heating system. Now, don't panic. On the next slide, there will be a few formulas. But there aren't too many formulas in this presentation, and these two are essential. The heat power that is being transferred can be calculated as the product of flow, in this case mass flow, M point, the temperature difference between supply and return, and the influence of the fluid, that's the Cp. We call it heat capacity, but we come to that in a second. The transferred heat energy is what ends up on your energy bill. This is the amount of water pumped in a certain period, so the mass, multiplied by the temperature difference and the heat capacity. So you could compare the heat power with your speedometer and the thermal energy with your odometer in your car. The heat power is important for the dimensioning of the system, while the thermal energy ends up on your bill. Now, here comes the definition for heat capacity from Wikipedia. Unfortunately, your slides are a little bit slower, so I'm reading it instead. The specific heat capacity symbol, Cp, of a substance is the heat capacity sorry, I was disturbed here. The specific heat capacity of a substance is the heat capacity of a sample of the substance divided by the mass of the sample. Informally, it is the amount of energy that must be added in the form of heat to 1 unit of mass of the substance in order to cause an increase of 1 unit in its temperature. In other words, the specific heat capacity describes how well a fluid can transport energy. How much energy do I have to apply to increase the temperature of 1 pound of water by 1 degree Fahrenheit? That's the definition for the BTU. So, the ideal heat transfer fluid has, of course, good heat transfer capabilities. That means a high heat capacity. It is cheap and available. It has a low viscosity. It is long-lasting, and it has no negative environmental effects. Anyone have an idea what this could be? Yeah, sure. It's water. But in some applications, another feature is important. If it gets too cold, you could open up an ice climbing center in your basement. Obviously, the fluid shouldn't break your pipes when it gets too cold. Therefore, antifreeze or glycol is needed. So, let's see what the experts on cold climate can tell us about the use of glycol. Let's have a look at the homepage of the University of Alaska. You should see now a diagram for the freeze point of ethylene glycol and water mixtures. On the x-axis, we see the ethylene glycol concentration in percent, and on the y-axis, we see the freeze point temperature. And as you can easily see, the more is not always the better. It makes no sense to add more than 60% of glycol, because then you get less freeze protection. The freeze point temperature is rising again. Now it's your turn. I want to do a quick questionnaire. Did you know that you can actually damage your system by adding too much glycol? There should be a questionnaire now on your screens, and I ask you to answer real quick. I'll wait a few seconds. Okay, 2 have answered so far. 9. Okay, let's have a look. At least 45% of you learned something already. That's good. So the webinar is worth the time you spent here. Okay, now when glycol water mixtures are cooled down, then first the water will start to freeze, creating a slurry. That is not good for the heat transfer, so your pump doesn't really like it, but the pipes will not burst if you have an expansion tank. So please check if your application really requires freeze protection or if maybe burst protection is enough, because in that case you could use a lower glycol concentration, and that's actually 5 to 10% difference. Now, on this slide, I'm going to badger you with some pretty nasty diagrams. Sorry for that. But it is important and necessary that I show them to point out the difference between water and water glycol mixtures. We already talked about the specific heat capacity, the ability to transfer heat of the fluid. On this diagram, we see the specific heat capacity for antifragic N, which is a ethylene glycol-based antifreeze. On the y-axis, we see the temperature. On the x-axis, we see the temperature. On the y-axis, we see the specific heat capacity, and you see different lines for different concentrations. I marked the line for water in blue, and I marked the line for 60% of glycol in green. Now, as you can see, the heat capacity for water is around 4.2, and with glycol added, 60% of glycol added, it goes down to about 3. That means we lose about 25% of heat capacity, or the heat capacity, the ability to transfer heat, is reduced by about 1/4. Next, we take a look at the density. The density of water glycol mixtures, again, you see here a diagram. On the x-axis, the temperature, on the y-axis, the density. There are different concentrations, or the different lines. Blue is again water, and green is 60% of glycol. As we can see, with water, it starts at 100 degrees C at around 0.96, and it ends up at 1.1 for 60% glycol at around 0 degree Fahrenheit. So the density reduces or increases actually by about 14% through the use of glycol. Last, we take a look at the viscosity. This time, again, on the x-axis temperature, y-axis is the viscosity, and the different colors is water, and the different lines are different concentrations. Green is 60% of glycol. This time, on the y-axis, we have a logarithmic axis. And we see that the viscosity of water at high temperatures is about 0.2, while for a glycol, 60% glycol, at low temperatures, it rises up to 20. That means the viscosity changes by a factor of 100. Now, what does this mean? What is viscosity? Now you should soon see a video. The viscosity is the thickness of a fluid. For example, honey has a higher viscosity than water. Viscosity is quantifying the internal frictional forces that arise between adjacent layers of fluid that are in relative motion. We will come to that later. So, now we got the fundamentals behind us. Let's get more into practice. Let's move on to the applications. Where is glycol used? Basically, whenever you are in cold climate and part of the system is outside. So that could be solar heat collectors, rooftop units, cooling towers, whatever is out on the roof. But glycol is also used in district cooling, either for cold production and storage. On the left side, bottom left, you see an ice storage, but sometimes also in the cooling distribution networks for the energy transfer to the customer. But if temperatures allow, try to avoid it, because you will soon understand why. We take a look at the circuit with the chiller and the heat exchanger again. From a hydraulic perspective, both the heat exchanger of your fan coil unit or your air handling unit and the evaporator of your chiller are long pipes creating a pressure loss. Now the pump power can be calculated as the product of the volumetric flow multiplied with the pressure loss. Remember, if we use a water glycol mixture, the heat transfer is reduced because the heat capacity is reduced. That means to have the same heat transfer, we have to increase the flow. Let's assume a system with about 50% glycol with a supply temperature of 40 degrees Fahrenheit and a return temperature of 56 degrees Fahrenheit. That means we need about 30% more flow. But also the viscosity is a lot higher. Imagine squeezing a honey bottle. You feel the pressure then. And therefore, it's creating a much higher pressure loss in your system that the pump has to work against. Therefore, in the end, we need about 3 times the pump power for the same energy transfer in this application that I just showed. So, stop throwing money out of the window and use only as little glycol as necessary. Now, let's talk about glycols. There is not one glycol or one antifreeze. There are products based on ethylene glycol, products based on propylene glycol, or completely other fluids. But modern heat transfer fluids are complex mixtures of water, glycol, oxygen scavengers or corrosion inhibitors, and anti-germ and anti-fouling components. There are dozens of manufacturers, and they all want to earn money. And each one has various fluids, all with different compositions for specific applications. For example, we have one manufacturer here that has 12 different fluids in his program. Here I would like to insert another short questionnaire. Do you use ethylene glycol based fluids or propylene glycol based fluids or others? Please answer now. There's really a big delay between what I'm showing and what you see, I think. So I'm waiting for a few seconds. Okay, now the answers come in. Yeah, Well, that's interesting. Different than what I expected. It's about 43% ethylene glycol-based fluids and 70% propylene glycol-based. As far as I know, in Europe it's the other way around, but yeah, interesting. Okay, but glycol can also change during its usage period. There can be aging or degradation. That happens mainly in solar applications. Due to thermal overexposure, the fluid becomes flocculent or clumpy. But there can also be a pressure loss in your system. And sometimes someone just adds water. In that case, you're diluting and your freeze protection might not be given anymore. Another topic is mixing on site. Usually, the instruments used to measure the concentration are not very precise, and to be on the safe side, people tend to use too much glycol, so they use a too high concentration. Sometimes they also add further additives with unknown effect. Last, also the fluid manufacturers can do changes. They can change their recipe, either to optimize their cost or because there are new environmental laws on the ingredients. So for example, a Dowcal from 2008 might not be the same as a Dowcal from 2020, even if the name is the same. I'm a bit curious. Has anyone of you ever added water to a glycol system after a pressure loss? And are you buying premixed fluids or are you mixing on site? Now you should have a questionnaire again. So I'm waiting for a few seconds for you to answer. Now the answers are coming in. Yep. Okay. You should now see the result. There was at least several hundred people, and we see that it is quite common that people add water. I don't want to condemn it, but it is changing the fluid. Now, question regarding premixed fluids and mixing on site. Please answer that. Okay, not so many are answering that. I'll just continue. So it's about 50-50. Also interesting for me. So now we got the second chapter through, and now we come to the insights. During the fundamental session, we learned the formula for the heat transfer Q point. So measuring the temperatures is pretty straightforward. Anyone can do that. The Cp for water, the heat capacity, is almost constant, around 4 kilojoule per kilogram by Kelvin, or 1 BTU per degree Fahrenheit and pound. But measuring the flow is the challenge. The only true mass flow measurement for liquids is Coriolis flow meter technology. But that's pretty expensive. That's kind of like using a Lambo to deliver pizza. If you got extra money, go for it. Now I gotta wait. Otherwise, was spoiled. Okay. Sorry for the delay. That's why in HVAC systems, the common way is to measure volumetric flow instead. Mass is density multiplied by volume, and mass flow is density multiplied by volumetric flow. The density for water is known, about 62 pounds per cubic feet, or 1,000 kilogram per cubic meter. So again, we have our mass odometer and our mass flow speedometer. Now, there are several methods to measure volumetric flow. But at Belimo, we decided to go for ultrasonic flow measurement. I'm waiting a little bit because I think there's still a delay. So let me explain how that works. Assume a nice meadow with a river flowing through. Romeo is on one shore at his tent, and Juliet has her tent on the other shore. Now as Romeo paddles across the river, he's really anxious and rowing fast. And he has the current to help him. When he paddles back away from his Juliet, he's a lot slower, because he doesn't want to leave her, and he has the current against him. Now, maybe you ask yourself, what has this to do with the topic of the webinar? Well, now we see the same in a more technical environment. We have a pipe, two ultrasonic transducers that can send or receive ultrasound. That means they can act as a loudspeaker or as a microphone. The upstream transducer, Romeo, sends an ultrasound package to the downstream transducer, we call it Juliet, which is accelerated by the flow through the pipe. When the downstream transducer sends an impulse back, it is slowed down by the flow. Now, what does this mean for the technical implementation? In the following slide, you will see how it's implemented in our large meters, sizes 2.5 to 6 inch. We see a pipe, we see the two transducers, and we have the diagonal design for the sound path. Actually, in those large meters, we have two parallel sound paths to be more accurate. On our smaller meters, sizes 1/2 inch to 2 inch, we have a U-shaped flow path or signal path. We have the two transducers, and then the sound is reflected on those diagonal surfaces. So it's going down, around the corner, and up again. So as the ultrasound bounces back and forth, we measure the transit times, downstream and upstream. The downstream velocity of the sound package is the distance between the transducers divided by the transit time downstream. And that is the superposition of the speed of sound and the speed of water, so the flow velocity. The upstream velocity is measured the same way and represents the speed of sound minus the flow velocity. Now we can transpose those two equations and get the speed of sound and the flow velocity. But in the end, we need the volumetric flow, not the flow velocity. Well, that's easy. We just multiply the average flow velocity with the area of the cross-section to retrieve the volumetric flow. Now we take a look at the flow velocity distribution in a pipe, because the flow velocity distribution in a pipe changes from low flows to high flows, from laminar to turbulent. At low flow velocities, we have laminar flow. That means we have layers of flow in the pipe with a lot of friction in between, kind of like an onion. That means the layer next to the pipe wall has a velocity of 0, and then the velocity increases layer by layer as we come to the center of the pipe. And this creates a flow profile as we see in the upper picture on the left side. High velocity in the center and getting lower to the pipe walls. At higher velocities, we start to have small turbulences. You can see that in the upper picture on the right side, those little circles. These turbulences, they act like balls in a ball bearing, and they reduce the friction quite a lot. Therefore, we have an almost equal velocity distribution over the complete cross-section. The point where the turbulences occur is depending on the flow velocity and on the viscosity. Remember, viscosity is describing the friction between the fluid layers. But also, obstacles can change the flow velocity profile. Remember the river in the meadows with Romeo and Juliet? Well, in a river, the water wants to go straight. And if it has to go around a corner, most of the water follows the outer bank. Therefore, we have much higher velocities on the outer side of the river bend and low velocities on the inside. That's actually also the reason why you always find sandbanks or gravel banks on the inside of a river bend, because the smaller water just has less force to carry the gravel. Now, exactly the same thing happens within a pipe. Most of the water just follows the outer wall, creating and is therefore getting faster, and it's slower on the inside. Therefore, we get a misshaped flow profile after the pipe bend. Other causes for misshaped flow profiles can be, for example, temperature sensors or other inserts into the pipe, valves, T-splitters, and so on. This is why we recommend some straight inlet length before a sensor. You will just measure more accurate. And in this respect, inline sensors with a known geometry of the flow body can also influence the flow profile in a positive way and better adjust to the flow situation. Now you understand that the measured velocity that we have in our signal path is not necessarily the same as the average flow velocity that we need to calculate the volumetric flow. And there is also not a constant correction factor we can use, but instead we need to introduce a correction curve K. Now this correction curve is depending on the flow velocity, and this curve is empirically determined during production on the calibration rig. For each meter individually, by comparing and adjusting the meters under test to ultra-accurate and traceable master meters at many points over the flow range. You see the meters under test in the test section on top. Those are the orange ones, and you see the ultra-accurate traceable master meters in the bottom. Those are the ones we refer to. Now in the next slide, you see a schematic example of what such a curve looks like. At low velocities, we have the laminar zone, and at high velocities, we have the turbulent flow zone. And they have different correction factors. So, now we can come to the result. To measure the heat flow, we first have to measure the velocity. Then we can multiply it with the correction curve that we got from production. Then we can multiply it with the area of the cross-section, we can multiply it with the density, and we can multiply it with the heat capacity and the temperature difference. So now we got the heat flow, or the heat power. The Cp for water is known and almost constant, and also the density for water is pretty clear. So we got the problem solved. Yes, at least for water. But here comes the party pooper. When we at Belimo started to do measurements with Glycol with our newly developed meters back in 2010, we suddenly saw a huge deviation in flow. At low temperatures with Glycol, we had up to 30% error on the volumetric flow. That gave us quite a headache, and it took us quite some effort to understand the causes and even more time and money to find reliable methods to eliminate this behavior. The curves in this graph show the error on a flow meter designed for water, but being used with 50% Glycol at different temperatures. Well, the problem is the change in viscosity. For water, between 0 degrees centigrade and 100 degrees centigrade, the viscosity changes by a factor of 10. But with Glycol, from 0 degree Fahrenheit to 250 degree Fahrenheit, the viscosity changes by a factor of 100. And the viscosity has a huge influence on the flow situation in the pipe. Remember the fluid layers and the ball bearings. The viscosity of a fluid makes it really hard to compare flow situations. But Stokes and Reynolds, Stokes on the left, Reynolds on the right, came up with a solution for this during the late 19th century. They stated that flow profiles can be compared if the ratio of velocity to viscosity is equal. We call this term then Reynolds number. So at the same Reynolds number, we have an equal flow situation or equal velocity profile. Viscosity has an influence on the friction between the fluid layers and on the point where the turbulences start. Therefore, it influences the shape of the correction curve that we established during production. It basically moves the transition between laminar and turbulent flow on the flow axis. Now, when we use the Reynolds number as a reference for our correction curve instead, calculating with the known viscosity in our calibration rig, our curve becomes independent from viscosity and is valid for all fluids and temperatures. After we understood the physical background and we applied this method to our meters, we finally got the desired result and are now able to measure accurately even when Glycol is used as heat transfer fluid. On this diagram, we see measurements with the compensation active at different temperatures and with 50% Glycol. It's the same meter, equal conditions, but the error is massively reduced. So, to retrieve the heat flow with Glycol, we again measure the flow velocity. But this time, we apply the correction curve based on the Reynolds number. Then we multiply with the area of the cross-section A, we multiply with the density, and we multiply with the temperature difference and the heat capacity to retrieve the heat flow or the thermal power. Now, we have an influence of the glycol on the heat capacity, 25%, on the density, 14%, and from the viscosity, there we have a factor of 100, resulting in an error of 30% or an influence of 30% on the volumetric flow. That means we really must know the concentration of glycol we have in our system. Therefore, especially in case someone dilutes it, as we see, is quite common. The concentration and type of glycol is essential for accurate heat flow measurement. It is not enough to program a meter with a type and nominal concentration. They can be wrong. Due to inaccurate on-site measurement, due to on-site mixing, or due to dilution with water. Concentration measurement is the key to reliable and accurate flow and heat flow measurement with glycol. Now, how do we measure the concentration? This is something unique to Belimo flow sensors. We also have a patent on this, so I'm not going too much into details. But I explained before how we can also retrieve the speed of sound from the measured transit times. Now, the speed of sound and the temperature can be used to determine the concentration of the glycol in the system. Unfortunately, there's little data available neither from the fluid manufacturers nor from institutes like NIST or universities or so. That's why we at Belimo build up our own fluid database. We have top-notch analysis instruments to measure all the relevant parameters, so heat capacity, viscosity, speed of sound, and density, over a wide temperature range and at various concentrations. This was a huge investment for us, but we are convinced that this is the way to go. Because we have also looked into alternatives. Well, there's Coriolis meter technology. It's really good. It can even measure the density, but it is quite expensive. On the other hand, there are mechanical meters. They are cheap, but they cannot measure the concentration to compensate the heat capacity and the density, and they have a problem with dirt in pipes and the limited lifetime due to the wear of moving parts. Then there's electromagnetic flow meters. Here you see a schematic. Should soon see it. We have two coils creating a magnetic field in the pipe. Then the fluid must be conductive, and the fluid acts as a current in the magnetic field, and therefore it induces a voltage between the two electrodes, and the voltage is then proportional to the flow. Well, they work well, but they can have problems with magnetite, and they cannot measure the concentration to compensate the heat capacity and the density. There are also electromagnetic insertion sensors. If they are not sold with a pipe piece, but only inserted in a common pipe anywhere, they measure only the flow velocity at one point. And the influence of the flow situation is not addressed at all. So this results in a very, very poor accuracy on volumetric flow, even if they state a good accuracy on the flow velocity. So we're coming soon to the end. Here's your take-home messages. To measure heat flow or thermal energy in systems with glycol, do not only measure the temperatures and the flow, but measure also the concentration. Because together with the fluid temperature, it has a huge influence on the heat capacity, on the density, and via the viscosity on the volumetric flow. And that needs to be compensated for. Now, the right concentration saves you a lot of money. Water is the best heat transfer fluid. If you need glycol, think, do you really need freeze protection, or is maybe burst protection enough? So, does your system really run when it's cold, or is it not active when it's really cold during wintertime? Use, of course, enough to protect your system, so check your climate, but do not add more than 60% of glycol, because it doesn't help. It reduces the freeze point. On the other hand, use as little as possible, because glycol increases your pump power by a factor of 3. Okay, now I'm at the end of my webinar. Thank you for listening, and I hope you found it interesting and helpful. We have now some time for questions, and in case there are too many, I will definitely answer them by email during the next hours or days. So
thank you very much. Thank you very much, Philip. We do have some questions that have come in. The first one is, I learned that there are 2 types of glycol. Does it matter which one I choose for HVAC applications? And which one is the better heat transfer fluid?
Well, there's more than 2, but you're probably talking about ethylene glycol and propylene glycol. They are pretty similar, but ethylene glycol has lower viscosity, so it uses less pump power. On the other hand, it is toxic, and as I heard in some states, it's not even allowed. Especially in food applications, always propylene glycol is used because ethylene is toxic. That's the main difference.
Thank you very much. You said that insertion meters are not so accurate. Can you explain that in more detail?
Well, I showed on that one slide with the insertion meters that they measure the flow velocity in just one point. And if you install them somewhere, for example, after a pipe bend or so, you have no information whatsoever on the flow profile. So how do you want to integrate the flow velocity if you don't know the flow distribution in the pipe? So even though they may be stating an accuracy of plus minus 1% on the flow velocity, on the volumetric flow, the accuracy will be not above plus minus 5% or so.
Okay.
It's a different thing if you sell it together with a pipe piece and you know the flow situation within the pipe.
Excellent. Thank you very much for showing the schematics of heating and cooling systems. I noticed that the energy valve was always installed in the return pipes. Is there a technical reason for it, or can I also install it in the supply pipe?
Basically, you could install it also in the supply pipe, but usually in the return pipe, you have less harsh conditions. So if we're talking a cooling system, you will have the higher temperature if you're talking about a heating system where you, for example, have a supply of, I don't know, 200 degree Fahrenheit, then the return temperature will be lower, and therefore the meter will just last longer and will be not in such a harsh environment. So we recommend to have it in the return pipe.
Okay, thank you. You proposed to distinguish between freeze and burst protection, which is very appealing to me. However, I do not understand on how to profit from this. Does the indicated freezing point in the data sheet indicate the beginning of the formation of the slurry, or is it the point where my system is in danger of burst? In case it indicates the beginning of the formation of the slurry, how much lower can I expect to have till burst protection?
Okay. Well, if you look at the data sheet of a heat transfer fluid, usually there's a diagram showing the freeze temperature and the burst temperature. And in between, you have that ice slurry. And if you look at that diagram, depending on the concentration and the temperature, usually you can reduce the concentration of the glycol by 5 to 10% if you only need burst protection. And burst protection is enough if your system is not running during the winter time.
Okay, next question.
One thing I want to note there, usually the manufacturers of the liquids, they also state a minimum concentration that you need, because otherwise you have not enough anti-corrosion or oxygen scavengers additives. So you also have to pay attention to that.
Okay. Next question. You pointed out that many suppliers have a large range of glycol types. As far as I understand, they mix the glycol with water and additional chemicals. Is it correct that I select any type of glycol and the energy valve will automatically detect the concentration and apply the right concentration, or are there restrictions?
Our energy valve detects the concentration. Our current energy valve lets you select between the two main groups, ethylene and glycol and propylene glycols. So you have to choose between those two, and then the concentration is detected by itself. It's not an instant detection or an instant measurement. It takes some time because it's a self-learning algorithm, but after a few days it will be pretty accurate. Now our next generation product, which will come out next spring, will have the possibility to be even more precise by having, well, it will profit from that fluid database that we are building up. So there will be this distinct fluids you can choose from. And that database will also be enlarged over the time. And our new meters, the fluid data can also be updated if they are connected to our cloud service.
Thank you. I have heard that glycol is not so good for the environment. Are there alternative heat transfer fluids?
Yeah, water. That's the best one. There are also others. You could, for example, use just normal alcohol. That they start to use it now in Switzerland, but that was mainly a problem with customs and taxes, that it was not allowed to use such high amounts of alcohol, or so, yeah. So that's more a tax and customs thing. But normal alcohol mixed with water, about 15% alcohol, is actually a pretty good heat transfer fluid. Good viscosity data, decent heat capacity.
Okay. On that topic, what are the dangers of mixing glycol with water to proper solution in the field?
Pardon, I did not quite understand that. Could you please repeat it?
Sure. What are the dangers of mixing glycol with water, basically?
Well, you are diluting it. And, I mean, if you are mixing on site, you buy basically a pure fluid, almost 100% ethylene or propylene glycol with some additives of one of the manufacturers, Glycol or whatever, and then you add water. So that is what you want to do. You buy it 100%, and usually water is around on the building site. But once you have mixed it and set it to a certain concentration, and then people add water afterwards, then they just dilute it and they change the behavior. So the freeze protection might not be given anymore, and the parameters that have an effect on the measurement are also changing.
Okay, we have time for probably 2 more questions. What exactly do you mean by freeze protection versus burst protection?
I think we just had that already twice, so I don't know. Should I explain it again? I mean, when you need burst protection, if you really want to prevent that the fluid is getting rock solid, because then it will burst your pipes. And freeze protection means you start to have that slurry. The slurry will not damage the pipes, but you cannot use it to transfer heat anymore, because if there are ice particles, your pump will not run very well. So if you are not using your system during winter time, then the burst temperature is actually the one you have to go for.
Okay, let's take one more. Is there a thumb rule for power consumption for room cooling applications?
Pardon, I still, again, didn't really understand it. Is there a thumb rule for?
For power consumption for room cooling application.
No, I don't really understand the question. I mean, room cooling applications, what do you mean by that? I think it's probably better if you write that in an email, then I will come back to you and bring a more thorough answer. At the moment, I did not get what you are pointing to.
Okay. One last question. What % of energy can be recovered from flue gas exhaust of a boiler?
That's not really my topic. I don't know. It's, I mean, flue gas is nothing Belimo is into, and nothing I'm working on. So I cannot give an answer there. I'm sorry.
Okay. Well, we are right at the top of the hour, so any additional questions can be answered via email afterwards. And I'd like to close out with any closing comments if you have any, Philip.
Not a lot. I just want to thank the audience for taking part, and for also taking part in the questionnaires. That was also interesting to me to get a feedback. And yes, thanks again, and enjoy the rest of the day.
Thank you.